Welcome to Lesson 14.2, Properties of Limits. By now, I hope you've completed 14.1. You've read 14.2 with a guided reading sheet, and now before starting the assignment, the exercises, you're kind of viewing this to kind of get further clarification. We're going to look at a bunch of properties today, and we're not going to prove them until calculus, but we're going to hopefully help you understand them a little bit better, so when you're actually asked to find limits of functions, both polynomial and rational, you can do that. The two simplest properties in the lesson are found right at the beginning on page 918, and those were discussed in the guided reading assignment. If you have any questions, please email me. But let's get to the ones that have a little bit more punch to them. A lot of times students would look at this yellow box and try to go right to number 1 and not pay close enough attention to this. This kind of defines the notation, defines the functions, and kind of clarifies what's going on with these. We've got two functions, f and g. C is the value that x will be approaching. L is the limit of that function f as x approaches c. M is the limit of g of x as x approaches c. So that's our hypothesis. If this is the case, if we have some very simple functions and the limit of f is L and the limit of g is m, then these 5 properties tell us that if you want to find the limit of a sum of two functions, you simply find the limit of the sum of the two functions, which in this case would be L plus m. So in words sometimes we say the limit of a sum of two functions is the sum of the two limits. L and m are the two limits. Similarly, the limit of a difference is the difference of the limits. The limit of a product of two functions is the product of the two limits. And lastly, of this group, the limit of a quotient of two functions is the quotient of the limits provided that m is not equal to 0. If you have a function, if you're taking the square root of a function, then the limit will be the square root of the limit of the function L, provided that the function is positive when you're near c. The examples in the book, example 1 shows that and kind of leads us to this polynomial function property, which basically says that if you want to find the limit of a function, simply plug in the value for c in for x, and whatever value the function produces for c will be the limit. That's if you have a polynomial. So polynomials really are not, they're simple functions to evaluate limits for because the limit is what the value is there. Unfortunately for rational functions, it comes with this little clarifying statement, let c be a real number such that f of c is defined. So the same thing works for rational functions provided that f of c is defined. If not, we're going to have to use another property. So for additional example 2, which we can look at right now, let's clear this out. For additional example 2, let's say that we have f of x is equal to this rational function, x cubed plus x squared minus 8x minus 12 divided by x squared minus 8x minus 2. And we want to find the limit of the function, notice the notation, as x approaches negative 4. If you're thinking, well, what about the denominator? What's interesting, if you have your calculator handy, which you should, and if you don't have your calculator handy and you don't have your textbook handy, pause this video and go get that stuff. But if you do plug in negative 4 now for this, you can see that you would get a real number up top and a real number in the denominator. And just to save you the trouble, what we get is, in the numerator, we get the value negative 28, and in the denominator 18, which is more simply negative 14/9, and as is a decimal is negative 1.556. You can imagine if you did this with your calculator, you would see this number. You could probably convert it to that form, but using the property of polynomial and rational functions, because f of c exists, the limit is f of c. So our limit in this case is negative 14/9. So you might be wondering, when is it a problem? Well, for additional example 3, it will be a problem because what I'm going to show you now is a function that doesn't exist at the place as x approaches this value. So here, if f of x is equal to x squared minus 2x minus 8 over x plus 2, and you can probably figure out where we're going to find the limit. We're going to find the limit of f of x as x approaches negative 2. What is it equal to? Well, you'll notice that when you plug in negative 2, you get 0 here, and you actually get 0 there. So f of negative 2 is not defined. It doesn't exist. On your calculator, you'd see an error there. So what we have to do in this case, and let me just minimize this for a moment, is look at this property here, which states that it's the limit theorem. If f and g are functions that have limits as x approaches c, so we're presuming that this function has a limit as x approaches c. It's just we can't find it by plugging in c. Then if f of x and g of x are equal for all x's that aren't c, then the limit of f of x will be limit to g of x. Now, what's the function we have? We have f. You say, what's g? Well, let's bring this back up and we'll find g. We're going to try to find a function now that has values the same as f except at negative 2. And we can do that by looking at the function and rewriting it in a different way. That, well, I shouldn't use this notation yet. F of x is equal to, if we factor the numerator, it's x minus 4 times x plus 2. Here's again where factoring becomes very helpful. And the denominator is still x plus 2. If we're not looking at negative 2, if x is not negative 2, and when you take limits, remember we don't look at the value. I know you said, well, didn't we just do that? We can find the limit that way, but remember when you find limits, you're looking as x gets closer and closer to a particular value, not necessarily at the value. Although with polynomial functions we can find limits by plugging the value in, we're going to actually make believe that we're not at negative 2, because we're not. We're getting close to negative 2, but we're not there. So if we're not at negative 2, then these two values are not equal to 0, and they're a common factor, and we can rewrite the function f as now g of x equals x minus 4. Now this is an irrational function. It's a polynomial function. So if this function g has the same values as f except at negative 2, we don't care about that. So for that means we can then say, well, it's g of negative 2, because that's where we're trying to find the limit as x approaches negative 2, and that's equal to negative 6. So if the limit of g as x approaches g of x as x approaches negative 2 is negative 6, so is the limit of f. So if I go right back up here, that's supposed to be a circle around there. So the limit of f of x as x approaches negative 2 is negative 6. And our last example we're going to look at is additional example 4. You probably felt that example 4 was the most challenging one. So again, you may want to look at example 4 once you see my additional example. You might want to pause this now and take a fresh look at example 4 before even seeing this one. It's up to you. Try either one of those, but you want to kind of refresh your memory with what example 4 was like, because I'm sure you've read it. So what we're going to do is look at this particular example, which I'll bring up in just a bit. All right, so let's bring up this example now. If f of x is equal to 2x squared, find that limit. The limit we're finding is of a rational function. It involves it's a function of h. The independent variable is h. And I just want to point out to you, if we plug in 0 now, we're going to get, if we found this limit now, would be f of negative 3 minus f of negative 3 over 0. Yeah, if we plug in 0 for h, we're going to get f of negative 3 minus f of negative 3, which is 0 over 0. It's not defined. So let's at least evaluate it. And again, notice, remember from Precal that, or from algebra, when we want to find f of negative 3 plus h, that means we're plugging in negative 3 plus h for this x. So we're going to actually find that f of negative 3 plus h is equal to 2 times negative 3 plus h squared, and f of negative 3 would be equal to negative 3 squared is 9 times 2 is 18. Okay? And now when we write this minus this, we're going to write 2 times negative 3 plus h squared minus 18 all divided by h. Well, what is 2 times negative 3 plus h squared? Well, the perfect square of negative 3 plus h is 9 minus 6h plus h squared minus 18. All over h. Continuing to clean up the numerator, distributing the 2, 18 minus 12h plus 2h squared minus 18 all divided by h. Well, the 18 subtract out, so we're left with negative 12h plus 2h squared. And what I'm going to do then is realize we're trying to find the limit of negative 12h plus 2h squared divided by h as h approaches 0. To find this limit, again, when you substitute 0 in, you're going to get a value that's not defined. That requires us then to find another function in terms of h that has the same values as this function except at 0. And to do that, we're going to just look at the rational expression itself and factor out an h and have negative 12 plus 2h. 2h, pardon me, divided by h. Now, if we're not at 0, those can go and we're left with negative 12 plus 2h. The limit of this is the same as what we were asked to find as h approaches 0. As h approaches 0, we have a polynomial function now. The limit of this polynomial function as h approaches 0 is the value of the function is 0, which is negative 12 plus 0, which is negative 12. So our limit is equal to, the limit of this as h approaches 0 is equal to negative 12. Takes a little bit of algebra to clean it up, but that's how that's done. Again, revisit this video. Revisit the example in the text. Read through the lesson again, or you can jump right into your exercises, get feedback from your exercises as you complete the odds. You can check answers in the back of the book, submit your evens, and you can get all those files on the website. Good luck, and we'll see you in lesson 14.3.